Yes, thank you. And also thanks the organizers for inviting me. As you can see, and as this has been explained already, we are mathematicians, but we are sort of crossing the border all the time and love to implement algorithms and also to bring these things to the, well, from the point of view of a mathematician, real life, of course, deep application. And so we are also very glad to be involved into this READ project and to be able somehow to see that our algorithms and ideas which we invented are really then becoming practice. Let's see, sorry. So my task here, or the idea of this talk, was to give you a short impression of what the technology behind all of this really would look like. But this, of course, is a really big task. I could lecture like for hours. And so this is just a fake table of contents because I could speak about all of these subjects here. You saw and learned already a little bit, and from many of you, of course, know that these things are important. But what is more important is that these introductory words here sound like inspection, so I will, like a glimpse, give you some ideas which are behind and some impression of the results. Because you have heard already few of these application things, it might be a good idea to look at it a little more in detail. And so I really feel that the composition of these talks today makes it more senseful than it would be if you just saw my talk. So here is a true table of contents. I'll speak about these three topics in a detail and in a little more detail, and put what very often has been mentioned, the HDR engine, into one subtopic without diving into these details. Of course, we can discuss these topics all afternoon. Yeah, what is the framework I'm living and working in is, of course, that we start when already a whole lot of work has been done. Like here, these dots, I'm aware of that there's a huge lot of work already, but we start with something which we call layout analysis in a wider sense. So at least for this engine, of course, I assume that I have these, what we call writings. So finally, text blocks. This might be whole lines, which we usually process, or simple words coming from table cells, for instance, or from form fields, for instance, these things. So imagine we have a writing image where the text which we would like to recognize is already in. And then we put it to the HDR engine, and I should also mention that it is work of my whole group, like consisting now of 5 more people, and also we are working since years with a small enterprise which sits in Rostock now. The name is Planet, and you will see the word Planet from time to time here, or the logo, or also my live demo, which I can offer for the maybe lunch break here to look at it, is now residing at a server of this small enterprise. So, and finally, what is the end of all of this, of course, is the output, some textual information which comes out. This might be a word. It might also be that we have not just one word, because we are not completely sure. Many people love to have alternatives, and then, of course, we need some confidences. Well, mathematically, we would be glad if this bare probabilities, but it's just mathematically it's less. And also, it might only be a position. For instance, we today heard a lot about the necessity of this keyword search, and then we do not need the translation of the word or the transcription, let's say, not translation, transcription, of course. It's just enough if there would be a red dot showing there is a word London or whatever we are looking for. So that's the whole world, and this is a major contribution here, and I'm going to talk about 3 parts of these processes. First, layout analysis is, of course, more than just detecting the lines, but for us, it's now mostly important to see how these lines are detected. And I also picked topics which are related to what you will see in Transcribers, and what you already saw here are these lines which were surrounded by these blue kind of polygons, which show that that's the text line, right? And what we are doing first is that we try to look at positions where we can see something which pretends or should be a written style somehow. I love this presentation because I should explicitly state that we are not working on binarized images. So binarization was a big topic like years ago. We are not working on binarized images, which on the other hand does not mean that we are not looking at some 0-1 decision within the process at some points, right? So we are not working on binarized images, we are working on the real usual scanned images. And also, which I should point out here, that in our technology, these polygons are much more advanced. So what we are really looking for are these blue polygons, which are here in the image down there, and we are using what we call baselines. And so you will see the word baseline when you are working more and more in this area. These are these red lines, and then we are composing the polygons from these baselines. You might imagine that these baselines, of course, are not unique in the mathematical sense. It's more like a matter of taste where you put the baseline, right? And this already is a big source of, or danger of mistakes later on in the whole process, right? But as for networks, it's very important that they see the very same kind of polygons in training and in application. We now prefer to keep baselines in the text and then produce our own polygons. Finally, these are polygons. So now imagine we have subject to the future processing these, what we call writing images. So the original images, but polygonal parts extract. These are then somehow corrected and normalized. It's not very important. It's important for the process, but it's by far not important that we present to the computer images which we as humans mean should be perfectly written. Don't care. So for instance, we have the experience if you train a network and then you flip the whole page from the, what is it, not upside down, the other way, from the left to the right somehow. So the machine reads the mirror image of the writing. It can read it perfectly. It has no idea of what perfect writing in a human sense is, right? So don't care about that. So these things are not that important, but they have to sort of made in a unique way for training and for application. Then we do the recognition. I'll just show a few slides of depicting this was here, happens with the recognition engine. And the result is a matrix of results, which, for the purpose of these talks, I used to call recognition matrix. There is a sort of battle going on what the name of this matrix is. But as usual in science, this will develop, and at some point we'll have a term, right? So, and finally, I'll talk about this decoding procedure, which then finally gives you some textual output, what I already explained. So imagine now we have a pre-processed image, which now is known to the machine. What is important? Of course, important is to see that now, contrary or contradictory to what we had before, it is not possible to select what we we're calling single characters, right? This is the name of a German city. And if you do not know the name of the German city, or that's a German city, then we will probably have a hard time to detect that here we have 3 letters. It might be basically everything. So the very old idea of OCR is somehow gone. It's simply impossible, right? So what we then have is the new idea of segmentation-free reading. So in a sense, we are not detecting single letters, but we are sort of looking over the picture and try to figure out what letter might be there. At some point, maybe here we are sort of certain that we had seen the B, like maybe even the second time. We already knew here by some reason it were a B, but here we are uncertain. We left the B, what comes up is not clear. Then we depicted here with this tiny little dot. It appears frequent times. It's, for this talk, not that important. So imagine now we are sort of scanning, this kind of scanning, the whole writing, and picking up information. To make this work, we need to remember information. So for instance, at this point, we cannot really see from the tiny little window which is there, the blue window, that it will be a letter D. But we have to keep in mind this information. When we go further, we might be able to know that that's a letter D, but only when we remember what we have seen before. So keeping information while traversing the image now becomes a very, very important, crucial step or idea of the whole thing. Also on a higher level, context is essential. So for instance, if I put the very same writing here and everybody sees these problem places, if I do not remember context, I'll certainly not be able to see what kind of letters this will be. It could be an N or equally value U or whatever. Also here, this combination of 3 letters. Finally, in German, it's 3 letters, then it's completely unreadable, right? So if I do not show you the contents, what it has been, then it's completely unreadable. So keeping things in mind and keeping information while traversing the image is both on the top level of the whole word, or maybe even sentence, or on the lower level of every single character. Very important. We are also interested, it's also important to have the language contents and the restrictions which are given by the information that we are using in a particular language is also important, right? Nobody can see what this really means, this word, but if I tell you and you were aware of that, that's a German city name, then you will be able to detect that as the name of this city. Bad Doberan, by the way, is the name. But you could easily end up with something else. So that's what you usually see when you have these dirty OCR results type of thing, right? But that's not what we want to have. So there is applications like reading single figures or stuff like that, where you only rely on what you really see, but mostly the context is extremely essential. So that's what in the other talks already has been mentioned. You need to give us dictionaries, language, information, things like that. And as more as you give us and as more precise as these things are, the better the results will be. So we usually call this the comparison against these dictionaries. So for instance, what I already said is that we have a list of all German city names and we say, okay, now find the German city names. Then we end up with a final reading result. This might be a dictionary of some keywords. It might be other things. We are doing this writing processing now in a way which explains that you can read things also from the left to right equally well like from right to left. Because we are not only traversing the image like once, we are traversing the image like in this particular setup we are mostly using now like 4 times, from left to right, from right to left, and within some column, let's say, also from top down or from bottom up. These 4 directions will then fed into the network. And now I'm coming to the real network structure. I've stolen this image from the inventor of all of this. So the basic overall structure of these networks is pretty much like this. We feed in information, whatever it is. And I love this picture of the Arabic city names because I cannot Arabic, so I don't even know what there is. If it is not an Arabic city name, please let me know. But I'm not trying to put dangerous things here. We feed in these things to the network. Those are scanned in 4 different directions. These are depicted by the arrow here. And then we compress information by these levels, which are called feed-forward 10H layers in a sense. And this is what makes up the network, right? You have layers of different type of neural cells. I show you one of these cells in a minute. And these are for compressing information, because at the very end we cannot have information like an image information. We have to have the sign, the character, a symbol, whatever is written there. So we have to compress information. And then it alternates with something which is called the MD-LSTM. This is long short-term memory, and the MD stands for multidimensional. So that's exactly these levels where information from this type of scanning is retained within the cells and processed and remembered and so on. The end of these network things is something here, what here is called the output layer, or usually called the output layer. And the output layer, you should imagine, is just, let's say, a row of cells or lamps or whatever. And whenever the network believes I see a particular letter, then one lamp flashes and the other ones are more or less quiet, which does not mean 0, 1, but somehow it's like this. So we get at the very end of the network processing some highlighting of expected labels, as we see, mostly characters. So I promised to show you the LSTM thing, because it's also a Rostock contribution. This sort of network structure is used all over the world right now. this is some cells, so at least we cannot avoid some technical part in a technical presentation, of course. And the memorizing of information is the really important thing. And that's what I wanted to show you. Look at the blue arrows. The information that by such a cell is produced, either in its what we call interior state or also exterior state somehow, is in the next time step, while traversing the image, fed into the very same cell or also fed into other cells. So that is what, in contradiction to these neural networks which have been used like 10 years ago, makes these things recurrent. That's exactly what makes these things recurrent. And that's working in the sense of keeping, memorizing information. All these edges are filled with parameters, and now the next step is that we have to train such a network optimally, in a sense, that we compare the network output against these training data samples, and now we are back to the level where you users really also have to provide all these data, for instance, and the optimization goal is, of course, minimize the error. So what we are doing is nothing else than adjusting these parameters along the edges such a way that the output of the network optimally fits to what the network is expected to say, because we know the true answer in the training data, right? Just for a practical impression of a large application case, we are working like with 10,000 network cells. Millions of trainable parameters can be there, need not be, but if you're doing a big network, then yes. 10,000s of training data samples, which now are not pages or something, these writing images, right? In my world is the first point. And we feed all data into the network like 150 times maybe. So if you give us millions of papers or millions of pages, then it would take a time, and that's already what we know. Well, these 4 weeks here should not disturb anybody, because when you do train these networks from the scratch, then it might take as long as 4 weeks for training the network. But the idea behind Transcribus, for instance, is that you already can use networks which are maybe quite good for your time period, writing style, and so on, and then just make some additional training. So this is just the academic starting case. Okay, the network output then is this. It's just a graphical highlight. So what we have at the very end, the network tells us what might be the probability of a particular label, of a particular letter, on a particular portion of the network. The writing is here, once again the same. The rows do not completely correspond to the position where we are, but the dark places mean we have high probability. Gray means, we are not really sure, and white means negligible. There's almost zero. It's clear it's not that letter. And here we have just the alphabet, the strange dot in the first column, like for the gap, for instance, and things like that. So the network output is always a huge matrix of these probabilities. And probabilities can only be estimated, or better to say confidences, because mathematically it's not that it is really a probability, in a certain given world. And the given world is the training data you are providing, right? That's the whole thing. We cannot estimate anything if we do not have the training data world, which makes it able to count, for instance. Yeah, then the decoding, it's not too hard, much easier than the network component of the process. This kind of decoding has been known like many, many years, but the estimate of these probabilities was like 20 years ago not as good as it has to be for really making this kind of decoding successful. So that's why people like until 5 years ago did not deal with recurrent neural networks. These were really for some people also surprising success of a new technology, which were possible or were made possible by bigger computers, of course, and better estimates of these probabilities. Okay, so then we do nothing else than that we try to compare the network output against a word which we expect, either from the training data or another application I will show at the very end. So we restrict our search to something which is in the dictionary, I said German city names or whatever, or even keyword constructs. So for instance, nobody only wants to look for a particular single word. We also want to look for structures, right? And that's what we hide behind the computer science expression term regular expression. Okay, so just to have a small glimpse again of what we are doing, we try to find the best matching, of course. Best matching means, okay, we have the maximal probability, or the figures you will see in a second is vice versa, the minus logs of these things, so then it's a minimum distance to the goal, right? So if I now present in the next slide some figures, then the maximal probability which you expect is 1, but we turn the whole thing over and have the minimum distance, so the best thing is 0, just we reach the goal. That's another measure in a sense. And then we can also give you not just one reading result, but we can give you several alternatives, which are then simply ranked by probability. The best one on top and other ones in sequent order, how many you ever would like to have. Yeah, just again a practical example. So this decoding is very fast. So for instance, from the Bentham, we had 433 pages for this training data. That's 10,500 lines. And to look for just one keyword is done in 2 or 3 seconds on average. I mean, I'm now talking about just a desktop, a laptop, what we all have in the offices. And if you want to try to read one page and you give me a dictionary of 11,650 words, so I guess it's already a number of words, yeah, which is acceptable for a usual language, then it takes 8 to 9 seconds. So searching is not the crucial point. It's not really does not take a long time. Yeah, this is the table I promised to show you just to have another glimpse of the decoding technology. We use something which is called dynamic programming, so maybe one or the other has already heard about it or learned it. It's a technology which is very old, and it says, okay, find, while comparing the Bad-Doberan network output against the question, are you image the word Bad-Doberan? And then the answer says, okay, up to here I am the correct answer with the distance 0, which means perfect. And then we are again at this position, and I do not really know what now the answer is, and I have to pay for a certain amount. If you force me to say, okay, I'm the letter E, then I have to pay 0.79 whatever, and so on and so on. So if I want to make sure that this network, this image, or better to say the network output of this image exactly is the word Bad-Doberan, then I have to pay like 2.45, whatever it means. If I have other words and I have to pay more, then it's less likely that's the correct answer. If I have better words, then they are the correct answer. And so we are comparing and comparing and comparing. And because these comparisons are so fast, it really makes it possible to somehow read. Yeah, just a short impression of some results. These are not new to you, I know, because some of them we have already seen. For instance, here we have results from the Bentham once again, and I put here just to give you an impression the word error rate and the corresponding character error rate. You see we can read lines perfectly like this one, and also here we can read lines almost not really. Like if you have 80% words wrong, then it's somehow strange. But on the other hand, everybody who would really like to try to read it, this crossed out line, should be careful in insisting what the personal word error rate would be, right? There's portions which are not so easy. Yeah, this is just an enlargement. We have also a tiny little example here for illustrating how important it is to compare against a given dictionary. Already here you saw the difficulty in this, what we call Schaft S. I don't know in English what you call it. I don't know this, long S, okay. It's very typical for the Germans, these two different kind of S, but also in the English, in your English slide I could see it. And if you just take this, what we call raw reading, then it's just the result, what the network says is most probable. But if you force me to bring these things to a given dictionary, then of course I can correct my own mistakes. And I can, for instance, make this much better, like here, or instance, insert the long S because this long S has been used by that time in the text, and so on and so on. Or here, for instance, this is not even a German word, right? And introducing the S would be a German word. So that's easy, but it's only possible with a dictionary. So also keep in mind, having a good dictionary is essential. It's very essential and saves you much more or gains much more in percentage than everything before. Yeah, then the keyword highlighting. I'm really glad that today both my predecessors highlighted the importance of this keyword search. And now this is an example of this year's competition for keyword searching. This is a conference name here where we also had the could make it with the best results. And so we highlight these keywords here in the text, right? We highlight it in the image because there is a crucial difference to what we have heard before. We are looking for keywords, like this keyword spotting. So Günther tries to make the difference between searching and spotting in a sense. And the big difference is that we are not looking in the raw image, of course. Some people also try to look in the raw image. They show you an image of a word and try to find a similar image on the image level. Nor are we looking in the transcribed text, which has been the case in what has been explained before. So you make a transcription first, and then you look for the word London in the transcribed text. So that was what Günther presented, what is online in Transkribus, or will be very soon, now only in the snapshot version. We compare it against this confidence matrix output. So you pre-process the whole thing, and then you compare against the matrix. You can do very complicated multi-word queries, what I said, these regular expression things, and who has learned or is somehow used to this regular expression syntax can build very, very complicated queries. We have live examples for these. This is only a screenshot, but I promise to switch on the live example then. So if somebody is interested, we can, of course, during the lunch break, maybe continue looking at it. It's a catalog of handwritten index cards from the Rostock University Library. It's like 6,700 cards, which have never been keyed in, never been transcribed, nothing. But we are now able, in looking for keywords and keyword constructs in this particular catalog. It's not completely online because the university library in Rostock also does not have the computer resources behind, so we have the same problem. If then 5 people want to look, then the computer goes down. But for test purposes, we have. So it's really ongoing at the frontier of what is going on, really. Yeah, final word. We used to say now, use the term HDR rather than OCR to make completely clear that the old paradigm of looking for characters is gone. Of course, it's sometimes important to keep in mind that's a new concept behind it when you use a new term, right, and not using the old one. It's not very important what term we use, and it's also developing thing, like some people call it automatic text recognition or things like that. But I would only like to point out how important I personally find it to make sure that the brain itself now says, okay, we are not sticking with the old OCR. It's a completely new paradigm, this segmentation-free thing, for instance. Okay, thanks for your kind attention here. Once again, thanks for inviting me for this technical talk. And I try to bring this live demo also to live. And let's see, we should have a video from my friends from Planet, which already now, as I'm ready for answering question, does the same thing without typing me. So you can see what's going on there. And it's not fake, it's then live working. Okay, thanks, Philip.
Thank you very much indeed, Roger. That was frightening.